In this video, I'm going to demonstrate the operation of a op-amp that is set up as a comparator. Here I have a quad op-amp chip. In fact, it's the TLC 2274, and I'm powering that chip with a positive 5 volt side and a negative 5 volt supply. All right. I have one quadrant of the chip set up, or one quadrant of the one of the four op amps included in this chip, set up as a comparator. So the inverting input terminal, which is the second pin, I have tied to ground, or 0 volts. So the inverting input terminal is referenced to 0 volts, and the non-inverting input terminal right now is reading negative 5 volts, and the reason that is because I have the output I have the non-inverting input coming from the wiper of a potentiometer, where the fixed resistors of the fixed resistor terminals of the potentiometer are tied to positive 5 volts and negative 5 volts. So that way, by turning the potentiometer, I can vary the potential that is provided to the non-inverting input terminal between negative 5 and positive 5 volts. Now, from our derivation, we know that based on the ideal op-amp model, the op-amp is going to take the difference between the non-inverting input terminal voltage and the inverting input terminal voltage, multiply that by a very large number, and try to amplify that. But of course, the output is going to be limited to the supply rails, either negative 5 volts if it's a negative potential difference, or positive 5 volts if it's a positive potential difference between those two terminals. Okay, so right now, since the non-inverting input terminal is at negative 5 volts with respect to the inverting terminal, which is at 0 volts, that difference is negative. The op-amp is going to try to multiply that by a very large number, so that would be a very large negative output. But since it can't go to a very large negative output, it's going to cap it at the low side supply rail. So the output pin here, which is pin 1, is reading negative 5 volts. Now, as I change the input into the potentiometer, or as I rotate the potentiometer, my input into the non-inverting terminal is going to change, and I'm still at a negative voltage right now. Alright, so I'm at about negative 1 volt. Again, a negative value reference to 0 is negative 1 minus 0 multiplied by a very large number, so I still have a negative maximum output from my comparator circuit. As I turn the potentiometer a bit more, we will go into the positive territory. So the output of the potentiometer circuit is now positive 1.5 volts. Positive 1.5 relative to the 0 reference right here is going to be a positive difference. That positive difference will be amplified by a large value, and then therefore it's going to be capped at the high side input rails of the op-amp. Alright, so the largest voltage that it can produce at the output is the same thing as what we're supplying. So since this is a positive difference, it's going to be a high or positive 5 volt output. Now what we can do is we can use this as a trigger circuit, or a yes-no circuit, to determine if the voltage that's being supplied to the non-inverting input terminal is greater than 0 or less than 0. And what I've done here is I've placed an LED in the output path as an indicator for us. So as I turn this potentiometer now, I can see by looking at the state of the LED, if it's off, the output is going to be negative, which is not going to allow current to flow through that LED and cause prevent the LED from lighting up. So now I know that the potentiometer is turned to a position where it is going to provide a negative potential. And if I turn the potentiometer a bit more, now I can see that because the LED is on, we have a positive potential that's being that is being measured at the wiper terminal of the potentiometer. Now, through the magic of television, what I've done is I've replaced the input terminal, the inverting input terminal, um, with a voltage divider path here. So instead of tying that inverting input terminal directly to ground, now it's tied to a voltage divider, to the center tap of a voltage divider, and the resistors have been matched so that between 5 volts and ground for the voltage divider, at the middle of the voltage divider, we should be getting a about 2.5 volts. So right now I'm reading 2.48 volts. Being introduced to the inverting input terminal of this op-amp. So now, the potential that is being supplied to the non-inverting input terminal is positive 1 volt. So even though in the previous case this would have caused the output terminal to go high, now we're taking positive 1 volt and referencing that to 2.5 volts. So positive 1 minus positive 2.5 gives us a negative value. That negative value will be amplified or multiplied by a very large value, so the output pin should be going to the negative rail, the negative supply rail of the op-amp. So now this supply, or this output, won't go to the high side supply until it exceeds the supply, it exceeds the voltage that is at the inverting input terminal of 2.48 volts. Okay, so now we can shift the yes or no question from 0 volts to any potential that we're interested in asking the question. Is it is the potential at the non-inverting terminal larger or smaller than the potential at the inverting terminal? And we can do that, we can achieve that using a voltage divider circuit. So again, if I were to place my LED in the path here, we would have an indicator, a light indicator that tells us about the state of the wiper terminal, or the voltage at the wiper terminal of the potentiometer. So any value below 2.5 volts is going to result in the LED being off, and not until I turn it so that the potential exceeds 2.5 volts at the wiper terminal will the LED turn on. So about right there is where we first see the LED turn on. And if I check the potential at the non-inverting input terminal of the op-amp, we see that it's slightly a little more than 2.5 volts. And that's when the LED turns on. And if I move it until it just turns off and we measure the potential there, again we see that the potential at the non-inverting input terminal is slightly less than 2.5 volts, just as theory predicted that this, or that the ideal op-amp model predicted that this comparator circuit would behave.